you load the NHNES library. If you don't have it, install it, you load it. So now let's also load the data and check the structure of the data. So this is the structure of the NHNES data. I've already explained this in one of the classes we have previously. And we are going to filter for the gender, BP systolic average, and smoking status. Let's view this and see. So you can see this is what we have: the BP systolic average, the smoking status, and also the gender. So now let's create a binary variable for high systolic blood pressure. We're going to create a binary variable now that is going to categorize this based on this threshold 120. So those with above 120 systolic blood pressure, we categorize them as yes, that is high, and those with BP systolic pressure, we categorize them as no, which means it's not high. So we're going to do that and run this. And if we check the head, we can see that we have this high blood pressure systolic average no. You can see for all of these they are less than 120. So that's what we're categorizing. And we have NHNES data. We are going to omit the missing values. So by omitting missing values, if you check for it now, you are going to see that we don't have all those missing values again. Some rows are missing, so we are just removing the missing values. So now we already have our data. So now let's test for the proportions. Now we are going to do a test of proportion of males with high systolic blood pressure. For simplicity, we'll consider only male participants. So let's consider only male participants. We are going to subset just male, and n male, which is the number of male data of male in the row in the male data, we'll get that, and number of male with high systolic blood pressure also. So we'll call L male. We have 1759. We'll call N high BP. The number of male with high systolic blood pressure, we have 135. So proportion of male with high systolic blood pressure, now we're going to divide their number, which is 935, by 1759. So when we do that, we have 0.53. So now we are going to conduct a one sample Z test for proportion just by another value. We are assuming that we don't know this proportion now. And somebody told us that the proportion of male with high systolic blood pressure is 0.5. So now it's our work to now use the one sample Z test of proportion to see that. So this is the test. This is the function prop.test. And this particular prop.test function, it has various arguments. First of all, you give in your vector that you're trying to look at, and also the theta number in the population that you have. Then we have P, which is the proportion I'm testing for, and correct, which is false. And also you have this particular argument I talked about, alternative, whether it is two-sided, greater or less. I told you use two-sided if your alternative hypothesis is not equals to a value. But if it is less than a value, your alternative hypothesis, use less. If it is greater, you use greater. And we have correct. That means a logical indicating whether Yates continuity correction should be applied where possible. So this is, you can just decide to use this or not. So most of the times this is true by default, but I'm just giving it as false. Yates continuity, so we can just even decide to just remove it. So now let's run this and see what we have. You can see that our p-value is 0.0087, which means that we are going to reject the null hypothesis and the proportion is now 0.5. So let's make the proportion now 0.53 and see what do we have if we make it 0.53. You can see now the p-value is 0.9152, which means that what we are not rejecting the null hypothesis, that our our proportion is actually 0.53. We make it 0.51. What do we have also? We can see it is also closer to our true population proportion. That's what our p-value is 0.07437, which means it's higher than the our level of significance, which is 0.05. So we are not going to reject the null hypothesis. So this is how the proportion works. So now let's calculate counts for males and females with high blood pressure. So I'm going to separate the data by gender now. So I'm going to have a subset of the male data and that of the female data. We're going to calculate the various counts to find the proportions, the actual population proportion. We are just using this to explain the analysis we're going to be doing later on. So let's see the number of male is number of female. and number of high male with high blood pressure, and number of female with high blood pressure. Okay, sorry, so to be BP. So this is it. So if I said number of female by number of female with, okay, sorry, it should be number of female with high blood pressure divided by number of female. You see that is what we have, and for the male is 0.53. So for the female is 0.41. So these are two proportions. Now I'm going to conduct a two sample Z test to see now if we're assuming now that we don't know the values of these population proportions. So the reason why we are doing this is because somebody will be like, okay, why don't you just take the mean of the both samples? So we are assuming that that particular data set we have is a sample. So even though the mean might be different from the samples, in real life, from the whole population, the means, or for example, the proportions can be equal. So by doing this test, it will let us know that their true population mean is not actually equal. So it's not as if we are just like, okay, let's just take their mean from the data set and compare them. So we're just taking all their proportions from the data set and compare. The population proportion of the females is 0.413 or 0.414, while the population of the male is 0.53. That is in the sample. But in the population, it can actually even be equal. So that's just it. We are taking assuming our data set is a sample. So that is what we are assuming. So that means we are trying to see if the true population proportion or population is the same. So this test is going to show us whether that holds true. So the first argument, which is x, is going to be a vector of the total number of successes. So if it is for only one sample, you give 1. Earlier on, as you did, you can see we gave that of n number of male with high blood pressure. For here, we are doing two samples Z tests. So we are giving number of male and number of female with high blood pressure. Then for year n is going to be the number of male and female in the sample that we have. And this Yates is for Yates continuity for large sample. We are going to now run this. So you can see that we have a value 0.000. So this is just approximately less than 0.05, which means the proportions are not equal, as you can see even from the sample, which means that even in the population, the proportions is not also going to be equal. Now we can run our results. So you can see these are results that we have, the various results that we have. So now for test of association, now we're going to be conducting the chi-square test of independence between smoking and high blood pressure. We want to see if smoking has a relationship with high blood pressure. So we're going to do what we call a contingency table. We're going to create a contingency table using the table function by giving the vector of the smoking status or smoking noun variable, and also giving the vector of the high BP systolic average variable. So this is the vector we created earlier on that categorized BP into high or low. That is yes or no, whether it is high. Then we're going to create a vector of this. So let's view the contingency table. So let me go and change this particular. I want to change this particular. That is, I want to change it to high or low so that we can be able to differentiate it in the contingency table. So I'm just going to come here. I'm just going to make this high. And I'll make this low. So I'll come back now. We run the contingency table again. Okay, we're supposed to run this so that will reflect. Then we come here, we run the contingency table again. So you can see now up here we have our systolic blood pressure. Now in this place we have our smoking status. So in this situation now, this has already obeyed most of the assumptions on the chi-square. We have two categorical variables, and also you can see that they have high frequency expected frequencies. So we can use the chi-square in this situation. So I'm just going to run the chi-square test. It's just a function chi-square.test, which you just input your table. When you run it, you have this particular value. If your value is less than 0.05, as you can see it in this place, it's what this means is that you are going to reject your null hypothesis and conclude that there's a relationship between smoking status and high blood pressure. Then this is for the features exact test. I'm just going to be using that particular table as an example, though it doesn't obey the assumptions for Fisher's exact test. So I'm just going to be using that particular table. And you can see we have a p-value also, just similar results to the chi-square. So you can interpret it like that. So what you should always take note is that you should use the Fisher's exact test when, for example, in a situation whereby you are having 0 here, you are having 1 in this place, you are having 5 instead of any value that is less than 5 in most of the cells, then you can use the Fisher's exact test. So this is just about it. In the future, I'll try to do courses on categorical data analysis and go deep into it.